take a look at today's lesson. We're going to be looking at some new formulas, yay! Some double angle formulas. So we have three sets. We have a double angle formula for sine and cosine and tangent. I'm going to kind of walk through these. First thing students get a little confused about is what in the world is a double angle? And really it's exactly, what it sounds like. You basically multiply the angle by 2. So if my angle measure was pi over 4 and I wanted the double angle, sine of 2 times pi over 4 would just be sine of pi over 2, right? So it's just really truly just a double angle. It's twice the angle measure. And there are times when we don't want to work with double angles. We may want to have a single angle. Maybe our triangle is a single angle triangle and we need to work with that. So we have formulas that allow us to basically go back and forth between double angles and single angles. So our first one, sine 2x, is equivalent to 2 sine cosine. Unfortunately, I don't have any fun stories to tell you to help you memorize these, but this one is just 2 sine cosine. We do have, I do want to talk about this cosine 2x. Notice how there are three formulas here. Really, I just memorized the first one. I have enough formulas in my head, right? I have lots of formulas in my head, calculus formulas, all that kind of stuff. And so the fewer formulas I can memorize, the better. So I memorized cosine squared minus sine squared. If I want to generate the other two, I can. And I'll just show you what would you do. Well, notice how this one doesn't have a cosine in it. So I would use my Pythag. We know cosine squared is 1 minus sine squared. And we see that this is equivalent to 1 minus 2 sine squared. So all they did to come up with these other two is to use Pythagorean. So here I would get my 1 minus 2 sine squared. If I wanted to use that, that's what I would do. Well, what about the one that has just cosine in it? Well, let's say that so I want the cosine. Let's say I turn sine squared into 1 minus cosine squared. So we distribute the negative because we're great algebra students, right? So we'd have a -1, so see a -1 right there. Cosine minus a minus cosine would be cosine plus cosine, which would be 2 cosine, 2 cosine squared. So these two we can generate with Pythagorean theorem, or Pythagorean identity. All right, so I just memorized this first one. That's the one that I have in my memory banks. Then the last one, this tangent of 2x, looks a little bit familiar to our tangent addition and subtraction formulas from yesterday, right? A little bit. In the numerator, we would have depending on if it was addition or subtraction, either tangent A plus tangent A or tangent A minus tangent A, right? We'd have a sum or a difference. In the denominator, we had the 1 in the denominator. Remember that? We had the 1 and then the minus. Then we'd have like tangent A, tangent B, or tangent S, tangent T, whichever letters you're using. I do want to show you that these are perfectly related to the addition properties. So if we were to do tangent, I'm going to write it like this. Do we all agree that tangent of x plus x is the same thing as tangent of 2x? Right, that's the same thing. So I'm going to use the tangent addition property. I'm going to show you that it's the exact same. So my tangent addition property told me to do tangent of the first angle plus tangent of the second angle, right? That's my addition property from yesterday. And then there was a 1 minus. Remember, these terms were always opposite, the signs. Then we did tangent of the first angle times tangent of the second angle. Remember that? So what is this? Tangent plus tangent is 2 tangent. And 1 minus tangent times tangent is this. So see, they are the same thing. They are all related to each other. You can get to one from the other. Are we okay with that concept? Yes.
So if in the case we use this formula, would it be acceptable to say both?
Sure. Yeah. Both of them are fine. They're really quite helpful. They're going to be helpful to us in many different ways, with proofs and with different kind of problems I'm getting ready to look at. Are we okay with the formulas? All right, let's go on to the examples. So on this first example, this is similar to some of the things that we did yesterday. We are told that sine of 7/9 sine x equals 7/9 and x terminates in quadrant 2. This is where we get to draw triangles. So let's draw a triangle in quadrant 2. And I'm going to label that angle x because that's the variable that they're using, x. So we know sine is opposite over hypotenuse, so opposite over hypotenuse. We use our Pythagorean theorem to come up with the third side, which simplifies to be 4√2. We know it's negative because it's the x value in the second quadrant. So now we have the triangle that we're going to use to find the things they want us to. Now here's the issue though. This is a double angle. This is not a double angle triangle. This is a single angle triangle. We don't get to just multiply everything by 2 and everything is just fine. That's not the way that it works. So if we have a single angle triangle to work with, I have no choice but to turn this into single angles. I can't leave it like that and evaluate it. So I'm going to use my formula for sine, double angle for sine 2x is 2 sine cosine. That's what I need to do in order to use this triangle. I can't use it otherwise. So now our job is to simply read those values off of the triangle. So we have the 2 sine. We know sine is opposite over hypotenuse, 7/9, and they also gave us that value. Cosine is adjacent over hypotenuse, so that would be negative 4√2 over 9. Okay, now it's just a matter of cleaning it up, with lovely algebra or arithmetic. So what do we have? We have 2 times 7 times 4 gives us a 56, which is negative √2 over 81. And that's our first problem using double angles. Are we okay with that? Okay, let's look at the cosine double angle. Again, I have just one of them memorized. If you want to convert to the others, you certainly can. If you want to memorize all 3, that is perfectly fine. But I just have cosine squared minus sine squared in my head. Notice how close it looks to the Pythagorean identity. It's very close, isn't it? Cosine squared minus sine squared. There's a couple of differences. One is a subtraction instead of addition. And of course, cosine, knowing how cosine is, demands to come first, right? That's the norm. Cosine, double angle for cosine. Cosine gets to come first. So cosine squared minus sine squared. Hopefully that will help you remember the order, because sometimes students mix up the order on how that is generated. All right, so we need to read cosine and sine off of our triangle, which we actually already did in the other problem. So cosine, we discovered, was negative 4√2 over 9. But of course, we're going to have to square that because it's cosine squared, minus sine is 7/9, which, we're going to have to square. So when we do that, we know that the square root of 2 squared is just 2, right? And 4 squared is, negative 4 squared is 16. 16 times 2 is 32. And then I have 9 squared, which is 81, minus, then 7 squared is 49. So just one little bit more of arithmetic, and we get negative 17 over 81. And that's our second one. We okay with that? Okay. Our third example involves tangents. This is a double angle for tangents, so we're going to write that formula down. We hopefully are starting to remember that. I know we just saw it like a couple of seconds ago. So what is that? 2 tangent x over, right, 1 minus tangent squared x. So in this particular one, we're interested in tangent. So tangent, we know, is opposite over adjacent, right? Opposite over adjacent. So it's going to be 7 over, so 2 times will be 7 over negative 4√2. All over 1 minus 7 over negative 4√2 squared. Now we get to, notice I said we get to do lots of arithmetic. Yay. So let's just kind of work through it. So we have 14 over negative 4 root 2 over 1 minus. So we know 7 times 7 is 49. And then when we square that, we get 32. I'm going to continue to work it. I'm actually going to reduce the 14 fourths into 7 halves. So 7 over negative 2 root 2 times, well, let's go ahead and go this way, over, so this is 32 over 32 minus 49 over 32 would give us a negative 17 over 32. Then we divide the fractions by multiplying by the reciprocal. So you know me, I want to avoid big numbers, so I would actually reduce this 2 and this 32. That's what I would do. You don't have to. I would make that a 16. And then we get to multiply 16 times 7, which is 112. And a negative times a negative is a positive, over 17 root 2. Now I am perfectly happy with this number. Some of us really want to rationalize for some reason, and if you want to rationalize, you're certainly welcome to. You would multiply by root 2 over root 2, and your answer would look like this: 56 root 2 over 17. So either of those is fine. There's really no need to rationalize unless you just have a burning desire to rationalize, and then you are welcome to do so. Okay. We okay? So of course there are proofs about this, right? Of course. I mean, we're going to have proofs with double angles. I hope that every single person in here recognizes this is not sine squared plus cosine squared. Your algebra teacher would be so terribly upset with you if that's what you thought. This is a binomial squared, right? We would have to FOIL it out. So let's do that. So it would be sine squared plus 2 sine cosine plus cosine squared equals right-hand side. I multiplied. I could have chosen to work on the right-hand side. I just really prefer to work on the more complex side, which I think squaring that is a bit more complicated. So this should hopefully, you know, we've seen this before, right? With the sine squareds and the cosine squareds, they're all separate in a jumble, but we know they equal 1. Remember, we've done that on several proofs before. It's a thing. So I'm going to take my sine squared and my cosine squared. I'm going to add them together and get 1. So 1 plus 2 sine cosine. And that's Pythag. Okay, so as a result of today's lesson, I think you recognize what to do now, right? This is a formula that we just looked at. This is for the double angle for sine. So I can use the double angle formula and convert it to sine 2x. And this is for double angles. Okay, how are we? We okay? Just add a few more formulas to our list. All right.